Welcome to My Favorite Universe. I'm Neil deGrasse Tyson. I'm an astrophysicist, and I'm director of the Hayden Planetarium in New York City, part of the Rose Center for Earth and Space of the American Museum of Natural History. And I'm here to present to you not lectures that are part of some curriculum, but in fact, I've combed the universe for just my favorite subjects. And I'm going to spend 12 lectures bringing those favorite subjects to you. These are subjects about which I've thought quite a bit. In fact, I've written about each one of them in the form of essays that have appeared in Natural History magazine. I've written many essays, and these are some of my 12 favorite. Organized in 4 groups of 3. The first set of lectures, On Being. What I mean by On Being is there are a series of 3 lectures there that present to you some of the machinery of what shapes and forms the cosmos. Machinery that we explore and investigate and discover here on Earth's surface, and find out that, in fact, the same properties of matter and forces and energy reveal themselves elsewhere in the cosmos, enabling science to be an enterprise at all. The fact that what happens on Earth happens elsewhere. The next set of 3 is all about the blood and gore of the cosmos. It's cosmic catastrophes, really. We learn about how black holes rip apart stars, and in fact, we take a person and toss a person into a black hole. Not really, but we describe what would happen if we performed that experiment, and that's pretty gory. But it is the real universe, and we need to know about that sort of thing. Also, in those lectures, we talk about cosmic impacts and what role they've played in the history of life on Earth. The next set of 3, we start at the beginning, the Big Bang, and move forward and present to you sort of the frontier of our understanding of the biggest questions of the cosmos. How did the universe get here? How has it evolved? How will the universe continue to evolve into the future? And we end on a set of 3 lectures which broadly refer to the search for life in the cosmos. It just so happens, anytime I'm on an airplane and someone finds out I'm an astrophysicist, I always get asked a series of questions, and the first one, 99 times out of 100, is there life elsewhere in the cosmos? So we've saved the best for last. We've saved the most enticing subjects for last, because everybody wants to know whether or not we're alone. And we'll tackle those subjects, and we'll do it broadly and talk about how to find environments where you might expect to see life. And not only that, if we find life, what might that life be like? Might it be like us, or nothing at all like us? So, welcome to this series of lectures, and let's begin. The On Being series is a set of 3 lectures on being round, on being rarefied, and on being dense. And these are 3 sort of properties of matter that, by describing them, take me places in the cosmos and have me describing objects that will show up again in later lectures. So it's not only a philosophical introduction, it's also an introduction in some measure by what objects are brought in to make the examples that we give. So let's begin with On Being Round. You've looked around at globes, at pictures of orbs. Why is so much stuff in the universe round? I don't know if you've ever asked that question, but now that I bring it to your attention, why not? Let's ask it. Why is so much stuff in the universe round? We learn, in fact, that the forces that make things round operate on small scales as well as large scales, because it refers to the energy of a body. And energy likes descending to the lowest energy state it can. So in other words, if you build a house of cards, the cards don't really want to stay built. If you jiggle it, they all fall down, and they get to a lower point on Earth's surface than they once were. This is profound. It wasn't simply that it's a shaky thing. It's that it's natural for things to want to go to the lowest levels possible. That's a natural consequence of physical law. You look around at all the round things in the world. Is there anything nature makes that's not round? Well, yes, there is. There are a few things. Just name a couple. Crystals are not round. Crystals have sharp edges. So there's some action going on geochemically that make crystals. And it's beautiful. Crystals are beautiful. That's an exception. Plus, you've got fractured rocks. Those have angles to them. But by and large, you look around in the cosmos, there are very few things that make angles. Things are round. And in the best of the cases, they make beautiful spheres. In that list, let's make a short list of round things. We've got soap bubbles. Soap bubbles are round. You had those as a kid, of course. Soap bubble, moons, planets, stars, galaxy halos, even the observable universe is round. It's a perfect sphere centered on us. And we'll end with that concept to learn exactly what we mean by the observable universe and why it's a perfect sphere centered on us. Now, the way this works is we have forces that want to shape the object in such a way that the surface is minimized. And what do we mean by that? Let's take a look at a soap bubble. So here we have a child blowing soap bubbles. We've all done this as children, and I wish more adults would do it into their later years. But soap bubbles are fascinating because no matter the cavity through which you blow this soapy liquid, out the other side comes a sphere. And what goes on there is, since a sphere is the shape that encloses the largest volume with the least surface, if a soap bubble wanted to be another shape, then the soap film would not be as strong as it is as a sphere. Because any other shape, it has to give more of itself to cover that surface area, making it thinner in one place and not another. It would just break. Now, this generalized feature can be revealed if I've got a cube here, conveniently. We take a look at the fact that on a cube, there are parts of the cube that are more distant from the cube center than others. So every corner is farther from the center than the middle of the sides. So in a way, that makes the sides kind of weaker. It makes the corners that are farther away. If this were an orb that had gravity, this would be some kind of mountain. And the forces that take over, that enable gravity to have made the planet in the first place, will want to make that mountain smaller. A rock on the side of the mountain will roll down and fill up the low areas. And this process continues until you get something that much more closely resembles a sphere and not a cube. Soap bubbles aren't the only thing that make spheres. Raindrops make spheres. No, there's a classical depiction of a raindrop that looks like a little teardrop. But in fact, if you were to watch rain, it comes out of the clouds and it falls down, it is a perfect sphere coming down. And what's holding it together? Well, there's this thing called surface tension, the surface of liquids. The boundary between the liquid and the air, that surface, the molecules kind of grab onto each other. And the act of establishing the surface of the liquid gives it a kind of a tension that wraps the liquid, so that when it's left to fall on its own, it wraps itself into a perfect sphere. Once again, making the most efficient shape it possibly can. You ever wonder how you make ball bearings? These little round things. Well, you can't lathe them. They're too small. One way to make them is you have liquefied metal, and you have an evacuated tube, and you take eyedroppers of this liquid metal, and you drop them down the tube. And as it comes down, it cools and hardens, but before it hardens, that drop of liquid metal turns into a sphere. It hardens, it lands down, and you collect your ball bearings at the bottom. That's one way you make ball bearings. Another way is if you are weightless in a space shuttle orbiting the Earth, you can just take your liquid metal, it's heated, and just squirt it out of the eyedropper. The liquid comes out of the eyedropper, floats in front of your face, makes a sphere, and it just hardens right there. In fact, you can make the most perfect ball bearings ever if you had a ball bearing factory in a weightless environment, like on the space station. So you're relying on the surface tension of the metal to bring itself into a sphere. And by the way, the only metal that's like runny liquid at room temperature is, of course, mercury. Not the planet, of course, but the metal. When I was a kid, we had little games where there's a mercury bead that would roll around and you go through a maze. But now we learn that mercury is bad for your health. It interferes with your development of intelligence as a child. But with these games, you notice that the mercury has such high surface tension, it pops into a sphere just sitting here on Earth. In fact, the surface tension was greater than that which would otherwise make it flatten out, than the force of gravity that would otherwise make it look like a bead of water sitting on a nicely waxed car. That looks like it wants to pop into a sphere, but doesn't quite have enough surface tension to wrap itself up into its little package, this little spherical package. Imagine a box of Cheerios and it's just a sphere. That would minimize how much box you would use. Or a can of beans, but spherical cans of beans. That'd be so cool. So I thought of advising the industry on this, but of course you realize there's another problem. Spheres roll. And so it'd be very hard stacking these things on the shelves. It would just be it would be a mess in the grocery store. So there are other factors that contribute to this, but it doesn't change the fact that if you have a spherical container, you have maximized the volume and minimized the outer surface, both at the same time. And nature knows how to do that beautifully. Let's ascend from Earth and think about the solar system and what kind of spheres we have going there. As I already alluded to, there's kind of a conspiracy of gravity and energy that gives you spherical shapes. The sun is one example. The sun, everyone's favorite star, is basically a perfect sphere. There's some structural form on the surface, but if you step back from it, it's a perfect sphere. It's a big ball of gas. Gas is easy to make into a sphere. Any part of the gas that's a little higher than the other part, it'll sink down, push the other side up. It might oscillate for a bit, but it's going to end up forming a perfect sphere. You know why? Because it all wants to get as close to the center of gravity as possible. The only way it can do that is to make the high places low. That minimizes how much total energy is expressed in that field of gravity. And again, that's why rocks roll down hills instead of up hills. They roll down hills into the ditch, and it'll stay there forever, unless you go and pick it up and put it up somewhere else again. So things have the tendency to fill in low places. Well, that's the sun. It's nice and big gaseous ball. Let's go to something that's 1/10 the diameter of the sun, the planet Saturn. Hold on to the ring for a moment. We'll get back to Saturn's ring, but look at that ball. It's a gorgeous spherical ball. It's 1/10 the diameter of the sun. It's also a sphere. Look carefully. Actually, it's a little bit flattened, top to bottom. We'll get back to that too. Because we'll learn that if something's not a sphere, it tells us something about what's going on in the environment of that object. Why something is not a sphere is more interesting even than why it was a sphere in the first place. Because it wants to be a sphere. And if it's not one, it's telling us something. Let's go to an object 1/10 the size of Saturn. Earth. Beautiful blue ball, looking like a marble in the sky. It's an image taken by Apollo 17. Let's go to 1/4 the size of Earth. We all know what's coming. 1/4 the size of Earth, we get the moon. Once again, a sphere. Gravity has no problems in a wide range of size objects turning it into a sphere. But you could ask the question, does gravity always win? Is there a point where gravity fails in its attempt to turn something into a sphere? The answer is yes. Gravity does fail. There's a point where the object is so small that the field of gravity is so weak that imagine you're looking at this mountain I described a moment ago, and you nudge the rock. There's not enough gravity to have the rock roll all the way downhill. And it just kind of goes a little lower, but that's about it. But otherwise, it's happy staying up there because it doesn't weigh that much. There are such objects. Let's go to something 1/10 the size of the moon. What do we get? We get 1/10 the size of our moon. We get a moon of Mars, Phobos. Phobos. Look at that poor thing. Craters, and it's got a funny shape, and I wouldn't want to have been there when that got hit or punched or whatever, but that's Phobos. You notice it's starting to not look like a sphere anymore. It doesn't have enough gravity to have wrapped it into a sphere in the first place. let's go even smaller than Phobos. 1/10 the size of Phobos, we get an asteroid, Gaspara, looking like a fine Idaho potato. Not a chance. It has rounded edges, sure, but it's not a sphere. Something's going on. It turns out if you're small enough, presence of those chemical bonds of the rocks themselves. So the rocks, either born a rock, they stay a rock. They don't get rounded out by the action of gravity. This is one asteroid, Gaspara. I got another one for you, about the same size. This is one of my favorites, called asteroid Cleopatra. This is a series of images of Cleopatra rotating, and we call it the dog bone asteroid. It looks like a dog bone, nothing like a sphere. Forces of gravity are helpless in its attempt to turn that into a sphere. By the way, it's also helpless turning us into a sphere. I am not a sphere, last I looked. The chemical forces in my body enable me to retain my shape even in the presence of gravitational forces within me that might want to shape me into a sphere. I'm small enough so that I'm in full control. But wait a minute now. The Earth picture that we saw is looking really spherical. We know that Earth has mountains and valleys and craters and cliffs, and there's the bottom of the ocean, and it goes really deep and really high. It's got texture. It's got surface. It's the soul of geology going on in the surface of a planet. So what am I saying that Earth is a nice, perfect sphere? Surely it's got this structure on it. Well, let's analyze that structure. Let's think about that. Okay? We've got these mountain ranges, and I come to my trusty globe here. You can't feel it, but I can, and I rub my fingers across it. And I'm coming across here Nepal, and there's some ridges there. You know, that's, of course, the Himalayan mountains. And I come over here to North America, and I feel the ridges, and up there goes the Rocky Mountains, the Alaska Range up here in Alaska, and I come down to the Andes Mountains. So the globe makers, in consort with the geologists, raise the surface of this globe in order to tell me where the mountains are. And say, sure, it would feel like that, you'll tell yourself. The answer is, no, it would not feel like that. You know why? Because let's go to the deepest part of Earth's crust. You know what that is? Right here, Marianas Trench, far away in the Pacific Ocean, 35,000 feet down. That's the deepest part of Earth's crust. How many miles is that? That's 5, 6 miles. 6 miles down. Okay? What's the highest point on Earth's crust? Mount Everest. How high up is that? 28, 29,000 feet. That's 5, 6 miles up. The total distance between the lowest part of Earth's surface and the highest part of Earth's surface is 12 miles. That's the length of Manhattan Island. You can drive that in 12 minutes, obeying the speed limit. Earth, as much credit as we like to give to the beautiful structures upon its surface, Earth, being 8,000 miles in diameter, it only has a 12-mile variation on its surface. It is as good a sphere as you could ever make in a laboratory. If Earth were shrunk down to the size of a cue ball, it'd be the smoothest cue ball ever made. You would not even know where the mountains are, where the valleys, the hills. In fact, if I were just some cosmic giant and Earth was out there in the sky, and I took my finger and rubbed across it, I would not know. I would not be able to tell what was water, what was land, what was mountain, what was valley. Because the depth of the mountains and the valleys would be the same as the depth of my fingerprint lines. It would go unnoticed. So, yes, gravity works. It works beautifully. We just happen to be really small and can't make the observation we need to make, that these fluctuations are only 1/600th the diameter of the globe itself. In the rest of the universe, we find some interesting things. We look around for places where objects are not spheres and ask, why not? Because we know nature wants it to be a sphere. So let's use this as the assumption that it wants to be a sphere and that we can learn a lot about why it's not. Let's take, for example, tidal forces. Tidal forces really wreak havoc on spheres. What are tidal forces? It's simple. It's the fact that if you're an object and there's a source of gravity over there somewhere, and that's tugging on you, that the side of you closer to that source of gravity feels more gravity than the side of you that's farther away. It makes intuitive sense. The closer you are to the object, the stronger its gravity field. So if I have some extent to me, this arm is going to feel your gravity more than this arm is, and it might try to stretch it out like this. In fact, that happens. The moon exerts tidal forces on the Earth. One side of the Earth is closer to the moon than the other. The oceans respond to that. And the oceans on this side bulge out, high tide. The oceans on the other side are not pulled as much towards the moon as these, and everything is sort of stretched in this direction and thinned in the perpendicular sides. So you have two low tides, two high tides. That's the tidal force of the moon acting on the Earth, turning it slightly out of sphericity. You know, this happens also in binary stars. You have stars, two stars in orbit around each other. The sun is only one star. We look around the cosmos, plenty of places where two stars are in orbit around each other. And if one of them happens to be a black hole, we have such cases, and another one is a blue supergiant or a red supergiant star, you'll learn about those in another lecture, it can become so large that some of its material will be funneled down towards the black hole itself. And as it fills up, the side closer to the black hole feels an extra tug. And the shape of the giant gets distorted, and it comes to a kind of a point as it funnels down onto the black hole. And that shape resembles a Hershey kiss, I like to think. And it's a distortion from what would otherwise be a native sphere. So once again, you have gravity, tidal forces of gravity changing the shape of things. Also, if you're an object and you think you're okay and you come too close to another object, it can rip you apart. You know, that happened with Saturn's ring. Some object, an asteroid, a loosely bound asteroid, or comet, some combination that came too close to Saturn, one side of it was closer to Saturn than the other, and it ripped it apart and scattered the whole thing into a ring. Eventually, those particles will fall out of orbit and Saturn will lose its ring. I'm happy to be around at a time where my favorite planet has the most beautiful ring in the solar system. Another thing that can affect your shape is rotation. Rotation. Jumbo gas clouds are what gives birth to stars. And anything out there has some kind of movement, but as it begins to collapse, there's something called the conservation of angular momentum, physics term. All it refers to is the fact that if you're big moving slow, big rotating slowly, as you get smaller, in order to compensate for having gotten smaller, you have to spin up. You got to spin up. We've seen this before. You know this happens. It happens every day on an ice skating rink. There's some ice skater who is turning like this with their arms outstretched, and what do? They bring in their arms, and what happens? They speed up. And let's try that. We can go slowly and then speed up. In fact, they could be much more effective at that if they carried weights in their hands, bringing more weight into their chest than just the weight of their fist. But that happens to gas clouds, as well as happening on an ice skating rink. The gas cloud collapses, it begins to spin up. And there's a resistance for material to flow inward in the plane of rotation. It's like that centrifugal force you're trying to resist, that force of the rotating platter at the amusement park. If you're in the plane of the platter, it's kind of hard to work in because it's trying to throw you out to the outer wall. That's kind of like we call it a centrifugal force, but it's not really a force at all. It's just your tendency to fly off. Fortunately, there's support back there so that you don't fly off the playground, the amusement park ride, but it's real laws, real forces of physics. So this rotation preserves the plane, but continues to collapse from top to bottom. And so it has the effect of flattening a system. Flattening a system. When you make a galaxy, big gas clouds make stars, they also make galaxies. Galaxies with 100 billion stars in them. So let's make a galaxy. So here we go. Here's a big gas cloud, and I'm going to make some stars early. So I make some stars, and now they have orbits that sort of come around like this, and that's fine. But the rest of the gas is still collapsing, and it meets in the plane of rotation. So it sort of kept its shape out here because that's the plane of rotation. The rest was able to collapse down, and we get a flattened system. There are galaxies that look like this. I've got an edge-on spiral galaxy. Look at that. That's a flattened system seen edge-on. Some stars retain their spherical distribution. That's the bulge in the middle. But the fact that this system is rapidly rotating meant in the plane, it's not going to collapse in the plane, but it did collapse top to bottom. So we lost what was previously a full sphere, and it went down to something flat as a pancake. Flatter than a pancake, in fact. The Milky Way looks like this. We are as flat as a crepe. It's about 1,000 to 1 diameter to thickness. A crepe. We've got stars above and below the plane of the Milky Way galaxy, formed before it collapsed. In fact, those stars are the skeleton of the sphere that was once there. In fact, I have a galaxy that has a much bigger bulge than our galaxy. It's called the Sombrero Galaxy. Look at that. It's beautiful. One of my favorite ones in the cosmos. This one, about half the stars formed before the thing collapsed and retained their spherical orbits, and the other half of the stars collapsed, preserved the plane of their rotation, and made the disk. So this one is a hybrid of the collapsed story. There's also general flattening. Simply, once you're made, if you keep rotating fast, you just get a little flatter. Earth is slightly bigger at its equator than it is at the poles. The equator, we make one day. The circumference is 25,000 miles, and we make one rotation a day. So if you're on the equator, you're moving 25,000 miles in 24 hours. So how fast are you going? You're going about 1,000 miles an hour if you're just standing on the equator minding your own business. Well, that puts a stress on the ball, and so it'll bulge out a little bit. So Earth has a bulge, an equatorial bulge. You might read about that. Not only that, Saturn has an equatorial bulge. That picture of Saturn we saw, Saturn is actually 10% shorter pole to pole than it is across its diameter, across its equator. Saturn also rotates much faster than Earth and is much bigger. So in fact, if you're standing on the equator of Saturn, you're moving 22,000 miles an hour. So that's going on such a good clip that in fact Saturn has flattened for having rotated so fast. And it becomes oblate. You have two words. Oblate means you're flattened. Prolate means you're sort of elongated. And I just think of hamburgers as oblate and hot dogs as prolate, if you need some examples. Especially when I'm hungry, I think that way. But what happens if you rotate really, 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 really fast? If you spun up Saturn even faster, you know what will happen eventually? Pieces of it will fly off. Imagine doing this experiment like with the Pillsbury Doughboy. That's it. You take him, you spin him, his arms fly off, end up on the walls. So you've got to be tough enough to sustain that rotation rate and to stay in one piece. There are objects in the universe that are so tightly packed and so dense that they can sustain a high rotation rate. They're balls of neutrons. We call them, sensibly, neutron stars. If they rotate and they pulse at us, they're also called pulsars. But they are neutron stars. And they're densely packed. It's the most dense state of matter known. Take the sun, compress it down into a ball about 10 miles across. That's the density of a neutron star. Let me tell you how dense it is. Scoop out a thimbleful of the material and put it on a scale, on one of these balance scales. Do you know what you have to put on the other side of that scale in order to make it balance? A herd of 50 million elephants. And that would balance one thimbleful of neutron star material. Or equivalently, take the 50 million elephants, cram them into a thimble, and that's the density of a neutron. Neutron stars. So, neutron stars are extraordinary things. Turns out, they have such high gravity that they can spin enormously fast without any risk of flying apart, like the Pillsbury Doughboy. In fact, we look in the universe and we find these pulsars, they're spinning 30 times a second. Then when we first discovered these, we said, we don't know any form of matter that can hold together and spin at that speed. And that's when someone was able to say, wait a minute, this is not ordinary matter. This is nucleonic matter. This is a dense ball of neutrons. And thus was the discovery of stars made completely of nuclear matter. Neutron stars, otherwise known as pulsars. And let me tell you how serious the gravity is on there. We have mountain ranges here where rocks roll down the mountain. Go to a neutron star. I put a sheet of paper on a neutron star and say, what's the thickness of that sheet of paper? The gravity is so strong that my effort to get on top of that sheet of paper, lifting myself to that thickness, will require as much energy as a rock climber on Earth ascending a 3,000-mile cliff. So that's some serious gravity going on the surface of a neutron star. And in fact, nothing has a chance of taking shape against the will of its gravitational force, and neutron stars are the most perfect spheres in the entire cosmos. Nary a mountain range to be found. My last point here is just the observable universe. It's simple. Light takes time to get from one point to another. And the universe has a birthday, 13 billion years ago. So every direction we look, the farthest we can see is 13 billion light years. 13 billion light years, no matter which way, because at that point we see the beginning of the universe. So our visible edge is exactly 13 billion years in every direction. And we're at the center of that horizon, just the way a ship at sea looks around, and it's the same distance from every point on its own horizon. Wherever it is, it kind of takes its horizon with it. Just as is true here in the entire cosmos. Let me just say that spheres are everywhere. They make a very useful tool. Now, we'll end with one of my favorite jokes. How do you make a cow produce more milk? Ask that of someone who's an animal husbandry expert. They might say, oh, well, change the diet of the cow, feed it better food, whatever. Ask that other question, that same question of an engineer. They say, well, fix the machine, change the suction rate. They'll try to change the machinery of the process. But ask that question of an astrophysicist who lives in the world of spheres, where anything that's not in a sphere is better off thought of as a sphere, and see how you adjust to make the real case. We would say, imagine a spherical cow.